In a world where data science holds the key to addressing humanity's most challenging issues, the Data Science Without Borders DSWB initiative has emerged as a bridge across Africa and beyond, linking countries to opportunities that would help governments harness the power of data for positive change.
Data Science Without Borders, starting from its name, is a very interesting project. I'm the lead with a couple of colleagues from very many partnering institutions. It's a dream that we wanted to see data science spread across Africa. We always know that Africa has been known to lag behind the Industrial Revolution, but with the advent of AI and data science, we wanted a project that will bring partners in the African continent. We'll look at institutions coming together to start to harness the power of this new technology, to leverage their data sets, and to build capacity in data science and AI to help Africa realize its dreams through data.
Launched in February 2024, DSWB continues to empower African scientists to champion data-driven solutions. By breaking barriers and strengthening systems, DSWB is driving innovation and creating lasting impact across Africa.
Many times it's been said Africa needs to leapfrog. Yes, we need to leapfrog. We need to catch up with AI. We shouldn't be left behind, but we need to fix the processes that will get us there. Look for the data. Where is it? Is it in good quality? Do we have the people who are going to mine this data, analyze the data? Do they have the skill sets? Do we have the infrastructure to actually do the analysis and punch all these analyses out there? And of course, the governance. You know that Africa has a lot of data governance, diversity. How do we get to that point? How do we learn from the different countries? And once we fix these important pillars, even as we leapfrog, it will be the success for effective use of data science and AI in Africa.
With passion, commitment, and collaboration, we can continue building a future where borders do not limit progress and where data science empowers us all.
You today. It's a little humbling. I'm going to tell you about our experience with synthetic data and with generating synthetic data. And I consider myself not a complete expert in this. I've worked with a lot of really good people, and I'm learning a lot in this process. And it's been very interesting and eye-opening. And so I hope to share some of what I've learned with you as part of this presentation. All right, let's see if I can, there we go. So I'm going to start out with an analogy, all right? And this is, so I'm going to talk about my experience generating synthetic data, but before that, I want to talk about my experience using artificial intelligence to create intelligence, AI, to create synthetic art. My in-laws had their 50th wedding anniversary this past December. And as a sort of gag gift or a joke gift on behalf of another son-in-law, I wanted to give my in-laws a framed AI-generated picture of them riding unicorns at a mountain lake. And so a friend and I, we went to Open Art, something on the web, which advertises itself as your creative vision elevated and realized by AI. And we gave Open Art a series of commands and a photo. So this is the input we gave. Those are my in-laws right there. And then we told Open Art to draw a picture of a man and a woman that looked like the people in this photo riding unicorns at a mountain lake. And then we did lots of iterations of this. So these are some of our output that we got. The one on the left is there's a man and a woman on a unicorns, but they're also on a surfboard in a lake, and they've got all these rainbows, and this guy has a horn coming out of his armpit. This one on the right, we've got a man that looks like a younger version of my father-in-law with a horn, but that does not look like my mother-in-law. So with a lot of iterations, and we ended up paying $29 for the month subscription to the deluxe version. This was the final choice. It's not perfect, but it kind of looks like younger versions of my parents-in-law's. That's a mountain lake that looks kind of like where they live. And I like that it still has the remnants of a horn on my father-in-law's forehead. All right, so my experience using AI to generate synthetic data is somewhat like that. So I've now spent over a year using multiple data generation methods, and I'm still sometimes I feel like I'm at the stage of putting horns on my father-in-law's forehead. I have glimpses of hope, and we're getting closer to generating synthetic data that looks like the real data, but I'm not sure we're completely there yet. So let me just quickly acknowledge that this is a team effort while I'm presenting. This is the technical team. Jeffrey Yang is a biostatistics PhD student who's working with me. Chao Yan is a biomedical informatics professor. Jo Hong Lee is a computer scientist student, and Brad Malin is a professor of biomedical informatics. And there's a lot of experience here with computer science and AI, and I have been learning a lot from them. This is an example of one of our weekly Zoom calls where they're trying to explain latent diffusion models to me, and I've learned a lot from them. All right, so what are synthetic data? Synthetic data are artificially generated data that are meant to reflect real data, but they're not actually real data. So a question that's often asked is adding noise creating synthetic data? And I'm going to say no, at least not for this talk. I'm going to consider synthetic data as being generated by sampling from an underlying distribution. So therefore, there's no one-to-one match from the synthetic data to the original data. So why would anybody want synthetic data? And I'm specifically going to be talking about synthetic HIV data because that's what I've done most of my work in. Well, partly because it's getting harder to share HIV data. There are international laws, there's privacy concerns, there's ethical agreements. For instance, I'm in the process of setting up a data use agreement to just pass on some de-identified data to another institution in the United States, Vanderbilt data to them. And it's such a hassle, all the paperwork you have to go through to do this, to set up these data use agreements. But we know that there are great benefits to sharing data. Open science leads to more collaboration, higher efficiency, higher quality and innovation. Funding agencies and journals are pushing for more open science. So synthetic data are perhaps a pragmatic way forward as these data are more easily shared. So I want to go through a few potential uses for synthetic HIV data. So the first one, and this is what got me interested in synthetic data in the first place, was what I call quasi-reproducible research. So I call a paper quasi-reproducible if the published paper includes one, the code that's used for the published analyses, two, synthetic data, and three, the results applying the code to the synthetic data. So I got into this because I wanted to make my papers reproducible, but to make them fully reproducible, you have to be able to share the original data. And I wasn't allowed to share the original data. So maybe I can share the synthetic data, and that will still help others know exactly how the analyses were performed, what we did. And so I've given some talks on this in the past, and we actually published a paper on this in the American Journal of Epidemiology in 2017, and I gave a presentation on it in Prague. That's a picture of me over in Prague back when I was young. And so here's an example of what I mean by quasi-synthetic data. This is a paper that we published in the Journal of the American Statistical Association last year. And table one is the table that appeared in the manuscript with the real data. Now we weren't allowed to share the real data, but in the supplemental material, we have all of the analysis code that was used for the original paper, but we also have some synthetic data where somebody could load it up, run the analysis code, and they'll produce this table over here, which is an identical version of the table one that's in the manuscript, except it's not formatted as neatly, but it's using the exact same statistical methods. So somebody can see exactly how we produce table one, and they can even try it on their own. And now you don't get exactly the same results because it's synthetic data, but you're getting things that are pretty close. And so I believe this is a way to be more open in our science. Another potential use of synthetic data is to facilitate education. It's nice, I teach classes, and it's nice to be able to train analysis techniques with realistic data, but you don't want to have to go through the process of getting permission to use the original data. I do this for my causal inference course where students have a final assignment to fit a marginal structural model to realistic data, and we use synthetic data based on our Cassinet cohort. And we've also used synthetic data in tutorial papers. So another potential use of synthetic data would be to get a head start developing analysis code. So maybe you still want the original data, but you can play around with the synthetic data. You can write your analysis code and your scripts so that while you're in the process of getting the approvals, you can be working on it. And so it'll move the process along faster. And it's even possible that maybe you'll just write the analysis scripts on the synthetic data and never have access to the original data, but you can then send your scripts to somebody who has access to the original data, or perhaps you could use some computing tools to run the analysis remotely. And so there's examples of synthetic data sets that are posted on the web from several really prominent research groups that are really, in my opinion, they're developed for this purpose. So for example, this is the UK Biobank. They have a website with a bunch of synthetic data sets, and they acknowledge values were randomly generated and the data set is presented without any warranty of correctness or accuracy. The data sets are therefore not internally consistent. But it still allows somebody to start playing around with the data set before they actually get it. Another potential use of synthetic data is data augmentation. And I say data augmentation to address health disparities, but it could also be just data augmentation because you do not have large sample sizes. And so the idea here is prediction models often perform poorly for underrepresented groups because models were built using data with few people from these groups. And so synthetic data for underrepresented groups may be added to the real data, thus making models fit to augmented data more representative. And this seems to work really well with imaging, especially medical imaging. I am slightly skeptical of the use of this with synthetic HIV data, but some groups have seen promising results. And I think it's extra promising if you can bring external data and create synthetic data based on the external data and then apply it to your smaller data set to augment it. I'm a little more skeptical when you're using your small data set to augment data from that small data set because it's sort of circular. I'm not going to be focusing a lot on data augmentation, but there is a lot of interest in this in data science fields. What I'm especially interested in is what we call hypothesis generation and hypothesis testing. So the idea here is investigators who are not affiliated with our research network can perform exploratory analyses with the synthetic data. And then if they find something interesting, they can approach the research network and ask to perform a similar analysis on the original data when there's an evidence suggesting an important discovery. And so it's, in my eyes, it's like I refer to it as the holy grail of synthetic data. It really could open HIV research to the masses to generate more ideas and findings. Now, with synthetic data, there's a sort of privacy utility trade-off. The better your privacy. So of course, with synthetic data, we want to preserve privacy, but we also want it to be useful. And often the better the privacy, the worse the utility, or the better the utility, the worse the privacy. And so ideally, we want to have something that's right up here where you have great privacy and great utility, but there's some trade-offs. And there's also interesting discussions in this field on how do we measure privacy, how do we measure utility. So, and I'm not going to get to too many of those details, but I do want to talk a little bit about how to generate synthetic HIV data. So synthetic data have been generated for 30 years or more using statistical techniques. And so, and it's kind of similar to multiple imputation ideas, if you're familiar with that. So this is how we did it for the synthetic data from the paper that I recently showed from a year ago. What we did is we fit a series of conditional chained models on the real data. So we fit a model predicting sex based on study site using logistic regression. Then using sex and study site, we fit a model predicting age. And then we fit a model for CD4 based on age, sex, study site, etc. And we kept growing our models until our final outcome model we predicted based on all variables. Okay. And so we have all these series of conditional models. And then to generate synthetic data, basically we randomly generate from these models. So we would randomly generate the distribution of study sites based on the original data. And then we would generate sex within study sites based on binomial draws, flips of the coin, based on our logistic regression model, this first model. And then now that we have synthetic sex, a synthetic study site, we can generate synthetic age from this model. And we keep building it up until we've generated all of the data in our data set. Now this works well for a single study with not very many variables, like 10 variables, which is what we had in our synthetic data set. But it becomes unwieldy when there are lots of variables. And what I'm going to be showing you a little bit later today, our Cassinet HIV cohort has somewhere around 200 variables in multiple tables. And some of the variables are collected repeatedly over time, like weight measurements, for instance, or CD4 measurements. And so the longitudinal structure of the data complicates things. Some people have followed like 2 visits, some people have followed 100 visits. So that challenges the things. It's possible to build nonlinearities and interactions in statistical models, but it's difficult to sufficiently explore the space. Another point is simulating from statistical models is simulating from something that you know. And so therefore it's not as good for generating new hypotheses because you're generating data from things that you already know because you created a model for it. So what about using AI for generating synthetic data? AI has been amazingly successful in many areas. 2 Nobel Prizes were given in 2024 for AI work. So why not use it for generating synthetic data? Well, so let me just point out, AI is really a big class of things. And you could say machine learning is a subset of AI. Neural networks are a subset of machine learning, and deep learning is a subset of neural networks. And most of the time when people talk about AI, they're referring to deep learning, but that's not necessarily the case. I don't have a lot of time to explain the details of deep learning, but let me just give you a flavor of it. So hopefully you're familiar with linear regression. You have an outcome and you have a bunch of predictor variables, X, and you can build a linear model. So a neural network, what you do is, it's illustrated here on the right. You still have an output, and then you can build a linear model based on that output, but you have a lot of different layers. And so we say like the outcome is a linear function of all these L's, but the L's themselves are linear functions with a transformation of all these K's. And then the K's themselves are linear transformations with a nonlinear function or transformation in between of all your original X's. So this is a neural network with two hidden layers, and it has a lot more parameters. So the linear regression model had 6 parameters, whereas this neural net, which is a very simple one, has 66 parameters. And then deep learning are neural nets with lots of hidden layers. And so using a similar structure with deep learning with 30 hidden layers, which would be not uncommon at all, that would give you 906 parameters. And so with a lot of parameters, you're able to see a lot more in the data. So more parameters, better fit, right? So if you have data like this, if you fit a linear model, you may be missing things. The problem is you can also overfit if you have lots of parameters. And so you want things that are generalizable. And so the way that this is done is typically you have training sets and validation data sets. You can split your data up and you train it in multiple iterations, fine-tuning the parameters, and you'll get better and better and better because you have lots and lots of parameters. But eventually you'll get to a point where if you apply your model to the holdout data set, to the testing or the validation data set, you start to do worse. And so the models are typically those that are chosen where you kind of see this inflection point. And so you'd probably choose the model around right here. So overfitting is something that is a concern with deep learning methods, AI methods. You need big data sets. Okay, so I want to give you a brief 30-second introduction to some of the most popular ways of generating synthetic data using AI. This is just give you a flavor of each of them. So one of them is variational autoencoder, VAE. Another one is GANs, generative adversarial networks. Another is large language models. And then finally, diffusion. So a VAE, what you have is an input. So here's a picture of my father-in-law. And you essentially send it through a neural network, and then you collapse it down into a latent distribution. And then from that latent distribution, you randomly draw and you go in the reverse directions. So this going one way is the encoder and going the other way is the decoder. And so you end up with output that looks kind of like the original data, but it's not exactly the original data. So that's VAE. GAN is you have two neural networks. So you have a generator which creates fake data, all right? And then you add it to real data, your fake data to the real data, and then you have another neural network which is called the discriminator, which tries to predict which one is the real data and which one's the fake data. And on the first iteration, it's easy to do that. It says, okay, well, this is real data, this is fake data, and then it gives that information back, and then the generator learns from that, and it creates new fake data that tries to trick the discriminator. And this process repeats itself over and over again until finally the generator is able to create fake data that's so close to the real data that the discriminator can't tell the difference. Kind of a cool idea. Another approach is large language models. These are things like ChatGPT. ChatGPT, an LLM is an autoregressive model that predicts one word at a time given the context. And so you could think of a patient visit as a long sentence. So there's a first visit when someone's enrolled and they get certain data, then the second visit and third visit. And so you could use kind of the same idea to sequentially generate patient history, kind of like you generate sentences. And the most popular approach recently is called diffusion models. And in these models, what happens is you have real data, and then you add noise along the way until you just have random noise. You can't see anything in it. And what you do is at each of these stages, you fit a neural network which tries to separate the noise from the signal. And then to generate new data, you generate noise and then you go backwards essentially, um, refining pictures or data so that you have fake data that looks kind of like the original data, but it's not the original. And so that's a rough overview of diffusion. So I've given you kind of just a quick overview of some of these approaches. I want to go through our experience using AI to generate synthetic HIV data. We've applied several different approaches, generative additive network scans using cross-sectional data, but then we focus more recently on longitudinal data. HALO is a large language model. SynTag is a GAN approach. Time auto diff is VAE plus latent diffusion. And then what we like best is something called MELD, which we've been developing, which is VAE plus latent diffusion also, but with a slightly different diffusion model and a few differences between time auto diff. And what we're doing is we're generating synthetic data from our HIV research network. As I mentioned earlier, they're about 60,000 patient records, 200 variables roughly in this data set, depending on how you count things. There are cross-sectional tables and longitudinal tables. Some people have one visit, some people have 120 visits. All right, so let me show you a little bit of our experience, and I also have a timeline. You can see how we've gotten better over time. So this is our original, the top row is our original data. This is weight, height, CD4 count, and viral load, and this is the distribution of it. So these are histograms. And then we also have original data that was holdout, so it's a testing data set. And the testing data set should look a lot like the original training data set because they're just randomly drawn from it. And so you see these are very close, but not exactly the same thing. So our synthetic data based on HALO was not doing that well, especially when you look at height. It seems like it's been driven by some of these outliers in the original data. And SynTag also had a problem with that. However, more recently, our synthetic data based on time auto diff and also MELD, it seems like it's getting the shape of the curves much better, although it's not getting as many outliers, I guess you could say. It's focusing on the center. It's not getting things further out. So that's what we're sort of seeing in our continuous data. With our binary data, our categorical data, what you could do is you can look at the probability of something happening in the real data versus in the synthetic data. So the unigram here, this is, so think of this as like the prevalence in the data set, in the real data set of tuberculosis and the prevalence of tuberculosis in the synthetic data set. But it's doing it for all of the categorical variables in the data set. And so you see MELD, this is our new approach, which is VAE plus diffusion. It's doing really well. SynTag is doing pretty well also. This other one is not doing as well, HALO, but it's not terrible. A little bit trickier is these bigram probabilities. So the probability of an outcome conditional on another outcome during the same visit. MELD seems to be doing well, but SynTag is having a harder time with that. And then this sequential bigram is the probability of an outcome conditional on an outcome during a different visit. And again, it looks like we're doing pretty well with MELD. SynTag's having a harder time. HALO's doing okay. So these are the sort of things we're looking at to see how well our synthetic data is matching the real data. You can do these things called t-SNE plots. I'm not going to go through the details of this, but essentially you have, this is mapping the synthetic data into some latent two-dimensional space. And you want, so this is the real data overlapped with the training data set. And so you notice that there's a lot of overlap. You don't see the blue and the red separate. This is what is ideal. This is our current best way of generating synthetic data. With MELD, we're doing pretty well. You can see some of these other earlier attempts. There's a lot of, it's easy to distinguish the blue from the red. This is the thing that we've struggled with the most. This is looking at time from enrollment until death. Um, and so these are cumulative hazards. And we've seen that a lot of synthetic data generators, they have a hard time generating realistic survival data. And so our first two iterations were Syntag over here, which looks like it does pretty well early on, but then it's generating a lot of things that are not very good later in time. And there's nobody in our data set who has followed for 60 years, but it's yet generating data along that lines. And Halo, another one, was completely missing it altogether. Some of our better approaches, though, this is time auto diff. It's using a VAE plus diffusion, and it's doing a little bit better, but still there's separation. This is our current favorite approach, MELD, and it's looking like it's getting it very close. So we're happy with that. You can also use these things for prediction. So here we are, um, we're training model on synthetic data. We're training models on synthetic data, and then we're trying to predict tuberculosis or cancer risk within greater than 6 months after enrollment, um, using on the original data. So we're fitting the model on the synthetic data, predicting on the original data. And so this would be the best you could possibly do. You'd expect the real data where you get, and this is the area under the curve, the AUC, so a measure of how predictive it is. Real data does pretty well, but our current favorite choice is doing pretty well there, actually. You lose a little bit of information. But interestingly, for the cancer prediction, it's actually beating the real data, which is kind of surprising. I'm not exactly sure why that's happening, but this is another way you could kind of see how well your synthetic data is doing. There's some other scores out there. I'm not going to go through the details of these. Basically, this one, low is better. Uh, this this one also, low is better. Um, and the thing to compare with is the testing versus the real data, because you shouldn't be able to do much better than that. And our current favorite is doing as well as the real data, roughly, although it's got a higher variance. Um, and it's doing a little bit worse on this latent clustering score. There's also ways of measuring um, privacy risks of synthetic data. And there's been a lot of people who've spent a lot of time thinking about this. These scores, to tell you the truth, I'm still wrapping my head around what they mean. Um, Essentially, you want this one to be close to 0, this one to be close to 0.5, this one to be something small. Um, in basically all of our synthetic data, the way we're generating it, where we're simulating from a model, we have pretty good privacy scores. And so we are preserving privacy based on the way we're generating synthetic data. There's always the concern with these deep learning methods that you could be generating data and just generating data that completely mimics original data, but we're not seeing that in any of our synthetic data generation. So just to kind of summarize some of our successes, synthetic cross-sectional data has generally been really good. We've been able to generate that very well. Marginal probabilities of categorical variables are similar to those of the original data. Our synthetic data are certainly of high enough quality right now for many purposes, like for quasi-reproducible research, for training, for developing analysis code. We feel really good about those. We still have challenges. As I've hinted at, it's hard to get associations between derived variables to closely resemble the original data. So the time from antiretroviral therapy initiation to death, for instance. We're finally getting to the place where it's looking pretty good. But I didn't show you some of our results where we then fit Cox models that predict associations between, say, CD4 count at ART initiation and time to death. And we're not doing as well there as I would like, although we're getting closer. It is a challenge to incorporate time into synthetic data, especially when there's a wide variety in the number of visits and data sets. And I think a lot of the synthetic data generators that are out there at this point, they've sort of skipped that issue. That they've only generated data where the data sets are the the records are all fairly similar. There's always challenges with generating synthetic data. It's almost like finding a balance between having models chase the outliers versus failing to capture the full range of the data. And there's also questions on what do you do with sparse data, missing data, et cetera. So we're trying to generate HIV cohort data that looks very much like the original data. So we are trying to generate missing data as well. And so to do that, we've been creating new variables, which are indicators of missing data. And that's kind of been our strategy. But there's other approaches out there, other thoughts on that. Right before I end, I want to talk briefly about ethical issues with sharing synthetic data. And we've been having discussions with people in our network about this. So one question is, what are the incentives for medical institutions or principal investigators to share synthetic data? Well, I think there are benefits, and we talked about those before. There are lots of benefits, open science. But there's also potential concerns that some of them have brought up to us. So one of them is data are valuable. Will good, publicly available synthetic data diminish the value of the original data? Could synthetic data expose a site's dirty laundry? You'll end up seeing things, if you release your synthetic data that looks a lot like your original data, will others see things that you don't want them to see about your site? Or could others take that, bad actors take your synthetic data and then publish things from it which you don't agree with, things potentially that could be harmful to the research endeavors? So I don't, some of these issues I'm not super concerned about, but I'm not the one that's collecting all the data. And part of my argument is I don't think synthetic data will ever replace original data. And so if I see something, find something in synthetic data, I'm still going to want to verify that in the original data. But that's my opinion, and others, there's a lot of discussion about this right now. Another question we've discussed is how should we share synthetic data? Should it be freely downloadable on GitHub for anyone, or should there be tiered levels of access? And right now in Castanet, we're planning to lean towards the conservative and have tiered levels of access. So somebody has to submit a very brief concept sheet so they know what they're going to be doing with it, and then we'll give them access. So it's not having to go through a heavy data use agreement process, but there will be a little bit of oversight. But that's what we're thinking, at least. And then there's also questions like, how do data privacy laws apply to synthetic data? No one really knows. We're just assuming that they don't, but is that a fair assumption? What do people living with HIV think about synthetic data? So these are all things we're thinking about, and others are. So my current conclusions: synthetic HIV data are useful for quasi-reproducible research, for training, for preparing analysis code to run on the original data. The quality of synthetic data does not have to be super high for these tasks. Synthetic HIV data may be useful for hypothesis generation, but that's not yet clear. And so synthetic data has to be of high quality to achieve that goal. That is our target, and it requires the use of AI generation. But when I got into this process, I thought, oh, this will be easy. I'm going to create some synthetic data that looks like a lot like the original data. And you can tell 2 years later, we're getting closer, but I was sort of naive to think that it would be easy to do this and that AI would provide quick and easy synthetic data generation. So let me just end by acknowledging my team, my funding. I'm very grateful for the funding and for the people who worked with me on this. And I'll leave it now just to answer any questions or for discussion. So thank you.
Thank you, Brian. That was such a wonderful talk. And I mean, the start with a beautiful prediction of the photos there. That's really, really interesting. Yeah. So yeah, so we do have 5 minutes remaining on the top of the hour. So there is one question on chat, and maybe we can pick one more, and then maybe we can conclude. But we do advise anyone who has additional questions to always type in the Frama pad, and you can always have time to respond to some of it. Yeah,
Okay, I'm
so
reading,
yes.
I read this question here: with the challenges with generating survival synthetic data, are there good methods for generating longitudinal data beyond just cross-sectional data? And I would say yes, they're getting better. And so we're hoping to publish one of our methods in the next couple of months to put it out there. It's that MELD approach. And some of the other ones I was also showing are okay at generating longitudinal data. But I think it's an active area of research where the models are getting better and better. Hope that answered your question.
Yeah, thanks. I think that the second one is just the same. Yeah. So even as you also already touched on the missing data indicators, just out of curiosity, can this be combined, like synthetic data solving missing data within the real data? Is it something that is possible, or?
Yes. If you think of multiple imputation, in a way that is synthetic data. It's just imputed data that's made up based on models fit to the observed data. And
Okay.
so those ideas, yes, can be extended to fill in missing data. And we're actually using some of the multiple imputation ideas to create synthetic data. So yes, there's a lot of overlap.
Okay, quite interesting. Do we have any question from the floor, maybe? One last one before we ask Miranda or Agnes to. Yes, there's one hands raised. Grace, to you.
Thank you very much. I'm just curious. Is synthetic data reproducible? Can I reproduce the same data set over and over again?
You would need to use a random seed number, a random number seed, and keep that the same, and then you could reproduce the same one. You bring up an interesting point though, because if you don't save the seed, then your synthetic data could be new with each iteration. And we actually recommend, and others have recommended, generating multiple synthetic data sets, not just one, because it's a better representation of what it sort of acknowledges the uncertainty you have in your models, your synthetic data.
Yes, exactly. Perfect. So also to mention that the next webinar series will be on fair data and federated analysis. And we'll have a talk from speakers from EABL and also UCT. So looking forward also for that webinar series as well. But thank you very much, Professor Brand, for making such a very informative talk. And I have actually learned a lot in statistics. Quite interesting with the models, and looking forward to practicing this.
Thank you very much again for inviting me, Michael. This has been great. Good invitation. And I appreciate the good work you guys are doing. So keep it up. It's an exciting
Thank
initiative.
you. Yeah, thank you very much. Okay.
All right. Thanks.
All
Bye-bye.
right. Bye-bye. All right.